Hello everyone, and welcome back to our class in Artificial Intelligence and Machine Learning in Finance. We are now at chapter 2.3, which deals with data generation. Now, we've already looked at data pre-processing, so why do we need data generation? Well, actually, in many cases, machine learning techniques rely on synthetic instead of real data for training and testing purposes. Why is that? Well, in several instances, we need to preserve privacy. We have confidential data, for example, on credit card usage, credit card fraud, etc. And it should not be possible to derive any conclusions on the origins of the data or on, for example, a certain person. So we need to preserve privacy, and in some instances we also need more additional data, or we have too few data to run our algorithms. So synthetic data is artificial data, usually created by algorithms, sampled via simulations, that should mirror statistical properties of the original data as good as possible, while not revealing information on real people. So we want to preserve privacy, we want to create training data for our algorithms, and we want to test our systems. This is why we need to generate data. Now, many training data sets are highly imbalanced, making classification tests difficult. And in these cases, synthetic data generation is particularly important for building accurate machine learning models. And we'll later on see how this actually works. So let's, at this point, look at three different ways how to generate data and what types of synthetic data we can differentiate between. The first one is fully synthetic data. And this is when the data is completely synthetic, is completely artificial, if you want to call it this way, and it does not contain any original data entries, any original observations, or values of certain variables. Thus, the joint density of the original data is estimated, and we sample random variables from the estimated density function. So in other words, we are only taking the original data, fitting a statistical distribution through the data, and then sampling synthetic data from that fitted statistical distribution. In this case, the data has strong privacy protection, but the truthfulness of the data is obviously lost because it's fully synthetic. Now, with partially synthetic data, this is the second possibility, we replace values of selected attributes that have a high risk of disclosure with synthetic data. Now, this could, for example, be, in the very most simplest case, could be that we replace the name, the first name and the surname of our observations, for example, when it comes to credit card data. Now, if we call everyone Mr. X, Mrs. X, it could be that actually this doesn't change the value of the data, but we preserve the privacy of the real people behind the data, or behind the original data. Now, disclosure risk is higher than in fully synthetic data, because you might imagine that it is often possible to identify persons not just by their name, but also if you take, for example, age, gender, income, and place of birth, date of birth, etc. So by combining different variables, you might still identify a person, so disclosure risk is higher than in the first case of fully synthetic data. And then we have hybrid synthetic data, that is, the data set is generated using both original and synthetic data. Now, each record in the original data is replaced by the nearest record in the synthetic data. So you simulate from a fitted distribution, but you try to replace the original data by synthetic data that is closest to the original observation. And this method combines good privacy protection with high utility at the cost of more memory and processing time. Obviously, this takes longer, but on a modern computer, this shouldn't take too long. How should we generate synthetic data? Now we have three broad concepts: generating data from a known distribution, fitting a distribution to real data and then simulating from that distribution and using deep learning. So what do we do in the first case? Well, actually, you simply take a statistical distribution, you simply assume that the data comes, for example, from a student T exponential or normal distribution, and then you simulate random data from this a priori chosen distribution. The difference later on to the second method, where we fit a distribution to real data, is actually that you simply assume the distribution and you assume it to be known. You make an assumption. For example, a normal distribution with mean 2 and standard deviation 5. This is an assumption that is not validated by any estimation, by any look at the real data. And if we now take this to the real data, make an assumption, let's say on the parametric form of the distribution, but we still estimate the parameters. If we fit the distribution to the data, then we get the second method. So if we have real data, you can determine the best fit distribution chosen from a given parametric family of distributions. Usually it's parametric. And you can then generate synthetic data by a Monte Carlo simulation. The quality of the generated data obviously depends on, first of all, on the selection of the parametric form of the distribution, and also on the estimation. So we might want to try a goodness of fit test. We want to check how far the fitted distribution is from the empirical distribution function. And last but not least, you can also use machine learning models such as decision trees, providing an approximation to non-classical distributions. For example, if you want to use a multimodal distribution, that is one, for example, that has 2 humps. And in these cases, overfitting might be an issue. You have to be careful that if you use very complex distributions, you might get overfitting. You might be fitting the distribution also to the noise in the data. And as a third method, we have deep learning. We'll later in this lecture see different methods from deep learning. I only want to mention 2 of these here. Deep generative models, such as variational autoencoder, VAE, or generative adversarial network, GAN. Now, VAE is an unsupervised method where the original data is first compressed by a so-called encoder into a more compact structure, and then the decoder generates a representation of the original data from the compressed data, and then the system is trained to minimize the differences between the output and the original data. As you can see from the word encoder, this is something that is also used in audio and visual compression. In the GAN model, we have 2 separate networks that are trained iteratively. In the first network, which is called the generator, this takes random sample data to create a synthetic data set, and the second network, which is called the discriminator, then compares the synthetic data with a real data set, and the generator network is trained to make discriminating between the generated and the real data for the discriminator network as hard as possible. In a sense, you want to make sure that the discriminator network, which could also be a real person, is not able to distinguish between the synthetic data set and the original data sets. This is obviously what you want to try to achieve when it comes to data privacy. No one should be able to determine whether this is the original observation or a synthetic one. And then this is also frequently used for generating image data. If you click on this link here, you can see the link here, you can watch a demonstration on YouTube for the GAN. I don't want to go into detail here, but you should know that you can also use deep learning algorithms for data generation. Okay, so we've now talked enough about data sources, data generation, data pre-processing, and next we will start looking at AI and ML methods with their applications in finance.